now or just wait? Okay, so do you mind? So JK, do you mind if we recorded your seminar?
Please go ahead.
Okay. Okay, great. Thank
Get
you.
started.
Yeah, good morning, everyone. So this is Jay. Today is my great pleasure to introduce our seminar speaker, my speaker, Dr. Jinkyu. As you can call him JK, Dr. JK Yang from University of Washington in Seattle. So currently, JK is a professor in aeronautics and also astronautics in astronautics department. So he got his PhD degree, same area aeronautics and astronautics from Stanford, and also a Bachelor of Science degree in aerospace from KAIST. I believe that's Korean Advanced Institute of Science and Technology, right? So yeah, before joining University of Washington, so he was a faculty in the University of South Carolina. So it's kind of close. He did his postdoc at Caltech. You see here, right? So he got a lot of awards, including the NSF Career, University of South Carolina Rising Star, and some Thinking Tank Team Awards. Also, his research are featured by many news reports. For example, the Reuters NSF News and the U.S. Public Broadcasting Service. So currently, his research more focused on the developing novel engineered materials and the structures. For example, the metamaterials, polonic crystal, and also non-conventional composites with application in aerospace and also mechanical engineering. So today he's talking to be about the origami and the topology, the two powerful ingredients for designing mechanical metamaterials. So let's welcome. Thank you.
Well, thank you very much, Jay, for the nice introduction and also for inviting me. I wish, I have visited your campus, in person, but well, hopefully in the near future. But nonetheless, I'm still very excited, and I hope that my talk can open some opportunities for future collaboration with distinguished faculty and students in your university. All right, so let me start with a very brief introduction of metamaterials. I'm pretty sure all of you have heard of metamaterials. So metamaterials basically manipulate dynamic responses, particularly energy flow. So the study had started from electromagnetics. So energy flow in electromagnetics is basically light. So if you look at, for example, a glass of water with a straw in it, what you see on the left is natural. What you see on the right is something unnatural. You need manipulation of light here. So for this, you need negative refractive index material. And interestingly, engineers have developed this locally resonant lattice structure, which is showing this negative refractive index material response. In the mechanical engineering realm, also there has been pioneering work to show, for example, negative effective density of material. So from the perspective of mechanical and aerospace engineering, the research of metamaterials is focused on enabling the control of mechanical energy flow. In other words, acoustic and stress waves in a novel way, unprecedented in nature. So if we can do that, then there's a whole lot of exciting applications. For example, we can do impact mitigation using metamaterials. We can do wave guiding, wave focusing for energy harvesting. We can even think about developing a new type of mechanical logic devices. So my question is, all right, metamaterials are very nice, but what can be design guideline? How can we design it, right? So there could be a number of different design principles, but I would like to introduce two very powerful tools, origami and topology, throughout my presentation. So first, origami. So using origami principle, I'll demonstrate how we can have very interesting, very abnormal wave dynamics, particularly in the nonlinear wave dynamics regime for impact mitigation. And second, I'll talk about topology. And for this, I'll focus on two-dimensional waveguiding, and I'll show how waveguiding based on topology can give us new features beyond conventional waveguides. All right, so let me start with the first one, origami. So origami is, as you know, art of paper folding. So I'm pretty sure you grew up folding these cranes or frogs, right? But you know, things are evolving nowadays, got a bit fancier. So crane, this is, you know, 21st century version of the crane. All right, this is the frog, which is looking much fancier, much more sophisticated. But still, the underlying principle is the same. These two sophisticated pieces, they still use single sheet of paper, and they still don't use any cutting. Just folding itself creates this type of beautiful patterns. Okay. All right, so I'll show you one example. This is a folding of origami by my collaborator, Tomohiro Tachi at the University of Tokyo. So let me play one more time. So he started this unfolding of this. He uses the clips, to make sure that faces are held together, but he doesn't use any scissors, doesn't use any glues. So when he started, you see he started under the natural light, but eventually it gets dark. So he has this light. So it took him about 8 hours, and requires folding of this kind of shape. So these dotted lines are valley folds. These solid lines are mountain folds. So if you print out this large piece of paper, and if you fold it, then you can also make this bunny shape of origami. So this is interesting because this is a origami's type of design principle, right? Started with a flat sheet, 2D, perfectly 2D geometry, but you can create three-dimensional geometry, even very complex ones. So nowadays there is software, like Tree Maker or Origamizer, and this Scorpion again is single piece of paper, and folding line can be, something that you can design by using this software. Okay, so this is very exciting field of research nowadays. So no doubt that people from architecture engineering leverage this origami principle, and also there is a origami inspired commercial product. If you see the sideline of this can, you see that it has a like origami pattern, right? Basically corrugation. So this is ideally by doing this, you can enhance the buckling strength of this can, and you can reduce 30% of the material by doing this design. And well, if you have kids, then you know how fast they're growing, right? So, well, if you buy new pants, doesn't last long because your kids are growing up. How about giving this origami pants to your kids? Your kids may not like it because, wearing the same pants over years may be not a good idea. But anyway, this is an application of origami for practical, clothes. Well, also, you can find origami patterns in nature, not only in this biological plants, but also animals as well, insects, wings. Nowadays, also origami has been providing keys for looking into the folding patterns of proteins. So this is another interesting field. But, with all this application behind, I am aerospace and mechanical engineer. So what can we use for origami for aerospace and mechanical engineering? Well, including Jay, you also have a faculty in your institute doing fantastic work, of applying origami for different applications in the realm of aerospace and mechanical engineering. That's fantastic. For me, I started to be interested in using origami for impact mitigation purposes. So impact is very classical problem in mechanical engineering, right? So this is a Falcon 9 SpaceX rocket. You have seen successful landing videos for reusable rocket motors, but they have gone through numerous failures. And that is oftentimes caused by the imperfect landing. Landing doesn't really do its job, then the results can be catastrophic. So can we have different approach for impact mitigation? So if you think about, again, landing structure, when impact comes in from the ground, you have to absorb impact as much as possible through this strut. Conventional structure, as impact comes in, you need structures like this metallic foam, which is crushed plastic fashion, to absorb impact. So the focus is, given the compressive waves, how much amplitude reduction can you have? That was the conventional aim. Can we think a bit different way? Interesting, novel way can be, given the impact coming in, can we convert compression to tension? Is it possible? Then what would happen? From the other side of the impact side, you're not going to feel the compression, right? If compression is converted to tension, instead of pressing the main body of the structure, it's going to pull it, right? So that is basically meaning you completely get rid of compression, completely get rid of the impact, right? But does it make sense physically? And if so, then can we do that, right? So again, the topic, the goal is converting compression to tension. Okay, so let me show you how we tackle this problem empirically, experimentally, and I will explain the physical underlying physics later, okay? So for that, we thought about this kind of a cylindrical origami structure. So this is origami cylinder, which has coupling between axial and rotational motion. As you see here, under compression, it rotates, right? And the modeling of itself is fairly interesting because this is not rigid origami, which means during the compression, these triangulated faces are undergoing facial deformation. So that modeling, I'm not going to spend time, but you can look it up, my reference here if you're interested. But this structure has been basically well known because upon the buckling of thin-walled cylinder, you have this kind of triangulated pattern. And if the structure is also under the torsion, then you get to have this type of deformation. And also well-known crystalline pattern is basically equivalent to this type of pattern, right? So this is, again, well-known origami cylinder. So what we are looking into is, why don't we align these cylindrical origami into single chain, apply compression, and if this structure can convert compression to tension, then we are basically achieving the goal that I have explained, right? So for that, we used laser cutter to cut this origami using art paper. And we also cut plastic pieces that will be placed between origami cells, okay? So the assembly was manual. I had a very talented student in assembling origami. So he was assembling about 20 cells of origami in a very consistent manner, okay? So I'm not going to talk too much about that, but again, I mean, depending on the crisp pattern, depending on how you design this origami pattern, you can make this very stiff, you can make this very compliant, you can make this monostable, you can make this bistable as well. So origami is, again, offering you design freedom to make unit cell of metamaterials behave in a way that you want, okay? All right, so you may be wondering, well, if you use origami for waveguide, then it may suffer from significant amount of damping. Yes or no? I mean, we have introduced compliant mechanism here. So upon the bending of these origami faces, instead of having fibers under, let's say, extreme bending, we basically made it kind of, having this ligament experiencing torsion. So we conducted hundreds of cycles of fatigue test on this paper-based origami cell, but we found that it is showing very consistent response, showing minimal hysteresis. Nowadays, I mean, we are using more of plastic pieces, which is even better. So that is how we are making this. So again, we have 20 cells of origami, and we need to apply strong impact, and we need to measure the responses. For measuring responses, we used 6 GoPro cameras. So 3 pairs, and each pair is measuring 1/3 of the structure. And later we basically reconstruct all the data that we have measured. And you see the green spheres here. These are for facilitating the tracking of these motion of the origami. Okay. Again, for the application of strong impact, we used electrical shaker, which is applying very strong pulse. But we only want to apply compressive force without restricting any rotational motions, right? That's why we had this 3D printed jig, which is allowing free rotation, but still effectively applying compressive force. Okay. So this is the experimental measurement. So impact comes in from the left-hand side, and wave propagates from left towards the right upon the application of impact. So here, red arrows represent motion of these markers towards right. Blue arrows are motion towards the left. So of course, upon the impact, you have compression of the first cell with red arrows, but any elastic medium is basically it tends to bounce back, right? So we have a bouncing back motion, tends to kind of move backward. But interestingly, red arrows, which is more like compressive waves, disappear very quickly, but what's left is more like blue arrows. So this is reconstruction of the experiments using this animation. This is not simulation, but this is experiment, okay? But we made deformation 2.5 times larger for the purpose of visualization. So again, at the beginning, we have compressive impact, but after compressive impact, again, elastic bouncing, elastic kind of a restoration of this each unit cell is following. But still, we have compressive wave propagating ahead of this. But after a while, see what happens. You see, compressive wave is basically lagging behind. Tensile wave is propagating faster. And at the end of the chain, what is the primary mode of wave? If I play one more time, at the end of the chain, blue colored wave arrives predominantly, which is tensile wave, right? Again, compression comes in. Tensile wave follows. But at the end of the chain, we have blue waves arriving predominantly, okay? So what is going on? What is happening there? So for that, let me show you the experimental results first. So this is space and time domain graph. So this is space. First cell experiences very strong compression. So positive z-axis is compression, negative z-axis is tensile strain. First cell experiences very strong compression. Due to the reaction, it has a negative dip. But compression is attenuated very quickly. Tension is propagating very robustly. At the end of the system, at the end of the chain, we have more like tension instead of compression, okay? Simulation, we can also verify that. So this is so-called rarefaction solitary waves, rarefaction solitary waves. So let me explain that, okay? So the physics underlying physics is, if you look at the unit cell here, if you do the simple compression testing, compression tension test, This is force displacement. I plotted 3 different curves, which shows that depending on different design parameters, it has different responses. But let's just focus on this red curve, okay? In the compressive domain, we find that the curve is not linear, okay? But interestingly, this curve is basically, slope is becoming smaller and smaller. So slope in the force displacement curve represents stiffness, right? So this curve means at the beginning of the compression, stiffness tends to be high, but as you compress more and more, it gets softened and softened. It becomes easier to compress. So from the standpoint of wave propagation, stiffness is enhancing the speed of the waves, right? But if you have nonlinear waves, which has component of small amplitude and large amplitude, small amplitude is having high stiffness, which is tending to propagate faster. Large amplitude has small slope, which tend to propagate slower. So these arrows represent the speed of waves. So if you connect these cells into a chain, then what happens is throughout the propagation along the chain, the base of the wave tends to get dispersed. The peak is tend to propagate slower. So eventually, this type of response from the nonlinear wave dynamics viewpoint is helping the dispersion of the waves throughout the chain. So it helps energy spreading. But what happens in the opposite domain, in the tensile domain? You do the same unit cell test, but now you pull it, okay? At the beginning, it has stiffness represented by the slope. As you pull it more and more, it gets actually stiffer and stiffer. It becomes harder to pull it. Then if you have this type of tensile waves, what would happen? Small amplitude domain, small slope, so it tends to propagate slower. Large amplitude domain, it will propagate faster. So it will basically form, it will coalesce, the wave will coalesce, build on each other, and it will create a shock. All right. So this is helping wave localization due to the effective strain hardening. So basically we have 2 different responses, right? Compression and tension. And this type of wave is, this kind of shock wave you can easily find in fluids, right? Fluids, this is a so-called solitary waves. If you have a narrow channel of fluid, and if you remove, let's say the wall of a dam, then the water propagates like tsunami. It propagates very robust form, very compact form, which is propagating long distance, even kilometers, without changing its shape. So this is basically nonlinear waves that we were creating in the origami structure. You can hardly see nonlinear waves in typical solids, because solids, what happens is typically very stiff and response is very linear. And you just need linear dynamics to describe most waves in solids. But what we have done through this origami design is we could leverage very large strain domain. In that domain, we could tailor the response to not only to make it behave linear fashion, but we can make it behave extremely highly nonlinear way. Then the unit cell we can tailor using origami design. Then metamaterial is what? Assembly of unit cells, right? So we assemble the unit cells into a chain. Then we can eventually, for example, build this type of equation. This is so-called KdV equation, whose solution is soliton. Okay, so this is well-known nonlinear wave dynamics equation in fluids. Now we can leverage this type of nonlinear wave dynamics in solids as well by using origami. So this is KdV equation solution, and the measurements and simulation, we are basically able to again create this type of waves in solids. So implication of this origami for metamaterials is it helps us to design unit cell, so we can manipulate unit cell responses and their corresponding dynamics as well. Okay, all right. So well, origami again, it may give impression that it's not really practical. It's made of paper, but my team is currently working on this type of let's say composite origami. Typically composite tubes very stiff, right? So it doesn't really break in a ductile manner. It breaks like glasses, right? But we can make it collapse in a very ductile manner using this type of origami. And also it helps, this type of chirality, we can use conventional filament winding technique, So origami also in the field of composites can be very helpful. And this can potentially, open new avenues for exciting composite research, okay? All right, so I just talked about the origami part, and let me move on to the second part of topology, okay? So let me speed up a little bit. Topology, when I first heard of topology, I was thinking about, are we talking about topological optimization like this? But topology that I'm going to talk about is mathematical topology. So you guys heard of the fact that coffee cup and donut have the same topology, right? What does it mean? If you integrate curvature over the whole area, divide by 2 pi, then it will give you an integer. That integer can lead to another integer, which is called genus number. That is exactly the number of hole. When you do the integration over the donut, when you do integration over the coffee cup, you're going to have integer 1 for both cases, okay? So how does it help with metamaterials design? For that, I need to talk about topological insulator. You might have heard of that or not, but let me briefly introduce that, okay? Topological insulator is material that's insulated inside, conducting outside. Well, what do I mean by that, When you think about insulator, you think about material like rubber. When you think about conductor, you think about material like metal, right? Topological insulator is like this chocolate. Inside, it's insulating, outside, it's conducting. But in fact, this is made of 2 different materials, right? But topological insulator is single material. And if you have topological insulator, electrons can travel freely on the surface. If you chop it by half, the newly created surface will offer that free traveling of electrons again. So this is a new type of material, and which has led to the Nobel Physics Prize 2016, okay? So I told you that this is mathematical topology, but how would it be related to wave propagation, right? So this is conventional band structure for wave propagation medium. So if you're not familiar with this type of diagram, this is nothing but X and Y domain means the direction of propagation of waves, with kx, which is wave number, which is 1 over wavelength, right? 2 pi over wavelength. Z-axis is frequency, right? So this band structure basically shows what type of wave modes are supported in a given structure, right? If you do integration of this type of band structure, like we call this Berry curvature, over specific point, then it can give you an integer, which is called Chern number, okay? So just like number of hole, which is integer, in the band theory, we can also have this type of integer, okay? But what's interesting is if you have material which has those different topological invariants, different integers between the material and, for example, between the surrounding medium, then the wave will be propagating only along the edges. So basically, you are characterizing the material from the bulk, from the unit cell, but you are governing the wave propagation along the boundary. So we call this bulk boundary correspondence. It tends to be a bit more physics oriented, but for this presentation, I'll cut the physics part and I'll focus more on the mechanical aspect, okay? All right, so again, how can we use that for mechanical wave propagation, right? Mechanical wave guiding, people have been working on this over decades. And this is simulation of acoustic waves from one channel, one part of this L-shaped channel to the other. Well, we can guide the waves successfully, but you see that the wave which is injected it tends to be lost, and you only have fraction of waves in the end because of, again, backscattering and loss of the waves, right? This is conventional wave guiding, which is made of the same type of medium at the interface. So you inject the wave and you tend to have the same type of, kind of similar shape, but with reduced amplitude because of the backscattering. The new paradigm using topology for wave guiding is, if you use two different topological medium, for example, one is orange, the other is donut, the wave will basically propagate without backscattering. And ideally, you're going to have the same wave shape arriving compared to the what is injected. So this is something that people in the wave community didn't know until the advent of topological insulator concept. Okay, but how can we realize that in the setting of mechanical waveguides, right? So for that, let me jump directly to our design. So we use this type of locally resonant pieces. So in the unit cell, we have 6 locally resonant pieces, and the mounting distance from the center is R. Lattice constant is A. If R is 1/3 A, then you basically end up having reduced unit cell. But if not, for example, R is larger than 1/3 A, then we have these 6 local resonance mounted in a sparse way. If it's smaller than 1/3 of A, then these local resonant pieces are mounted in a compact manner. I'm claiming that this large R is giving you donut, small r is giving you orange. Why? So this is again wave dispersion curves. Again, this is nothing but, I mean, depending on the direction of the waves, what are the frequency modes of the different types of waves, okay? This is flexural waves that propagating. So for the first case, when R is small, when we do the wave analysis, we can plot the eigenmode of these 2 points. And we see that due to the 2 different modes meeting at this degenerated at this single point, we can have 2 different wave modes, right? And the top mode is showing these 2 pairs of highlighted part. These highlighted part represent the deflection of the this unit cell, okay? And the bottom part is basically having 1 pair of this highlighted part. And what's interesting is if we look at the sparse part, we do see similar trend, but now the locations are flipped. We have 1 pair of oscillation for this upper dispersion curve. We have 2 pairs for the lower part. And this is basically, this D mode is migrating to to down here. P mode is migrating to the top. And then migration point intersection is basically so-called Dirac point when we have R equals to A/3. Okay, and I called the left-hand part is topological trivial, right-hand side is topological non-trivial, because if you think about the orbital of electrons, well, you might have learned it in undergrad chemistry course, right? When you have a spin mode of 1 pair, that's P mode, 2 pairs D mode. D mode tends to be having higher energy than P mode, right? Which is corresponding to the left-hand side, which is natural case. This is the right-hand side, it is flipped, right? So this is not natural. So that is meaning that it's topologically non-trivial. So these 2 modes, basically, again, back to this dispersion curve, even if you're exciting this structure at this specific frequency, left-hand side is oscillating with P mode, right-hand side is oscillating with D mode. So they are intrinsically supporting 2 different types of mode. That's why, due to that incompatibility, they support edge mode at the interface, right? So how can we realize it experimentally? Are you going to machine this and mount it, onto the plate? That's going to be very expensive and impractical, right? So what we have is, what we come up with is, we just drill 6 holes into plate and mount it into the plate, okay? Then this is a dispersion curve of this actual structure with the bolted mounts. It looks a bit more complicated. This is based on COMSOL simulation, but we do see Dirac cone generated, not only 1, but 2 of them. And we clearly also see P mode and D mode. And for this small compact shape, we have D mode located beyond P mode. But when it comes to the very sparse packing, then we have P mode now located in the upper frequency, D mode located in the lower frequency. Okay, so we do observe that mode crossing, okay? All right, so how can we fabricate that? So two of my students working hard on that, they mounted, the plate was drilled, using CNC machine. They did tapping all manually and they mounted all the bolts, found that the bolts are rattling, so they removed all the bolts, and now they are mounting bolts with super glue. So eventually they spent the whole week making this, and it took them, to use 1,300 bolts. That's a lot of bolts, okay? So this is experimental configuration. We have laser Doppler vibrometer, which is measuring the vibration of the plate spot by spot. And every time we are firing piezoelectric actuator, creating LEM waves, flexural waves onto the plate. So measure one point, fire, measure another point, fire, measure another point. So eventually we reconstructed all the experimental results, okay? So this is configuration. So we have two domain boundaries, one compact mounted, the other one sparsely mounted. And our goal is making the wave propagate along this domain boundary. Without the bolts, wave will propagate all throughout the direction, right? So the characteristic that we are expecting is, first, we expect to see the wave propagate very robustly. Even around the sharp corner, waves will not get reflected, okay? Second, we would like to see the directionality of the waves. For specific spin of the waves, we'll make it propagate towards one direction. This is due to the so-called hybrid mode. And this kind of a directionality of the waves is not something that we have been expecting from stress waves or acoustic waves. Because, for example, electrons, right? Electrons have its own spin nature. So that due to that spin nature, we can make specific spin propagate towards specific direction. But stress waves or acoustic waves, it's not really having intrinsic spin, right? But because of the P mode and D mode that I've introduced, and due to the hybridization of those two modes, we can have this type of effective spin nature, okay? So can we observe that? This is experimental results. Without the bolts, wave will propagate everywhere, right? But with this kind of two different configurations, we see the waves propagating along the Z-shaped domain wall, and even around the corner, you see very smooth turning, no reflection. And do you also see the spin nature of the waves? This is truly unique that we have not been leveraging in classical wave guiding studies, okay? So this is so-called pseudo quantum spinol effect. So again, which is mimicking the spin nature of the electrons, okay? So as I said in the beginning, electrons only moving along the surface of the material, right? That's the topological insulator, right? Electrons moving only at the boundary, which is basically the boundary between topologically non-trivial and topologically trivial medium, which is basically space at the outer world, right? So then only waves propagate along the edges, and with spin, it has directionality. We have created domain boundary in this Z shape, and we successfully demonstrated the wave guiding along that direction, okay? All right. So as you see here, we have a nice guiding here, and let me move quickly. So that was what I've just shown is how to guide wave in one-dimensional way. But using topological concept, we can also focus wave in 0D, which is one point of structure, right? So we had created another plate structure, and for this structure, inspired by Majorana bound state, if you have excitation of structure anywhere else, it will eventually move to the center point of the structure. So that will be very useful for energy harvesting, right? If structure is vibrated, vibration is happening anywhere else, eventually the wave propagates, wave is migrating into the center of the plate. That is basically topologically localized 0D position. And we have shown that experimentally that we can realize that focusing by using this type of structure. So this is the result after we excite structure apart from the center line but after a while, we see that energy localized only in the center, okay? All right, so that was the demonstration for 2D plate structure, but also in the 3D structure, we can also make the wave propagate along the surface, you know? So if using this type of structure, we can basically make a very quiet aircraft, you know, where noise doesn't really get into the cabin space. It only propagates along the surface so that we can have a very quiet aircraft, right? All right, so that is basically the second part of my talk. I was talking about the wave guiding by using the design principle of topology. So again, recap of my talk. First part, I was explaining how we can use the principle of origami for the design of metamaterials. And my specific application was impact mitigation. Second part was topology. By using the principle of topology, we can design metamaterials so that we have very unique capabilities in wave guiding. All right, so okay, so this is what I have today. I would like to acknowledge my students and postdocs who worked on this project. So the project that I've shown today is on origami and topology, which has been sponsored by funding agencies like this. And also the work has been collaborated with my fantastic collaborators listed here, okay? All right, thank you very much for your attention. And with this, I would like to I'm happy to have your questions and comments. Thank you very much.
Great, thank you, JK. Thanks for the wonderful talk. So any questions from the audience?
Yeah, can I have a question?
Sure, yeah, go ahead.
Okay, JK, yeah, excellent talk. I really enjoyed it.
Thank you.
Yeah, very nice work, very nice. I have two questions related about your rare fraction wave formation. Essentially, you convert the compressive wave to the tensile wave. So the first question is, how is the compressive wave converted to the tensile wave, right? Let's say for a continuous subject, the compressive wave would only convert to tensile wave if the other end is free, right? It will bounce back. But in this case, so how is it converted to the tensile wave?
That's an excellent question. So I said at the beginning that it's a conversion of compression to tension, which is in fact violating the principle of momentum conservation, right? So in fact, what's happening is do you see my slides? Yes. So upon the impact on the structure, you know, it always has, if its material is elastic, after compression, it tends to bounce back, right? So it has compression and tension component together. But overall, it will be, if you account for all the momentum, it will be more like compression dominant, right? So you do have compression and tension together at the beginning of this impact instance. Okay, what happens in this structure is compression. We are going to distribute the compressive energy, compression, over the space and time. So this is quickly, even within a few cells, compression is just all distributed. It propagates pretty widely fast over the space and time. So you only, in this simulation, for example, you only have small ripples left. So for example, in the ocean wave, for example, if you have let's say, if you throw a pebble into let's say, quiescent pond, then you will have basically kind of an excitation in the center of pond, but eventually linear waves all kind of moves around the pond. So that very sharp initial impact is gone. But tensile part is like tsunami. We leverage nonlinear dynamics here. Tsunami is something that is propagating very robustly. So that is basically conserved. So this is basically overtaking of tensile waves over the compression. That's basically the mechanism that's happening. And this origami structure basically was designed in a way that For compression, let it be dispersed. For tension, let it be kept in a compact form, nonlinear fashion like tsunami. So we kind of use two different mechanisms. Does it make sense?
Yeah. So yeah, I guess this is a specific or very much related to the Origami structure, right? I would say this will not happen for a continuous structure, right? So does it, right? If I have a solid structure, do you think this
Solid,
would
you
also
mean very
happen?
dense medium, right?
Yeah, dense medium, just a continuous
Right.
continuum.
Right.
Okay, so this I guess related to the Origami, the structure, but does it depend on the Origami material? For instance, yeah, the material, let's say the stress strain behavior, would that also matter here?
That's right. You got the point.
Yeah.
Yes.
Okay. Second question, very much related. Actually, also, you said the tensile wave, right, is going to move faster, right? It will catch up the compressive wave. You show the stress, well, you show the force displacement curve. There, I see the tensile is the tensile behavior is basically stiffen up, right? That is not common unless you are talking about well, let's say for continuum structure, you see the polymers may show this kind of behavior, elastomers, right? You see what I'm saying? Maybe you want to go to that slide where you talk about this this is slide actually, yeah. The bottom left part, right, is the tensile part.
Yes. Mm-hmm.
It goes up like that, but typically for a material to show this behavior, well, for continuous structure again, I only can think of elastomer will show this kind of stiffening.
Yeah, I mean, or for example, granular medium, like under Hertzian contact.
Okay, that might be also.
Yeah, but mostly they are, for example, granular crystals. They show this type of strain hardening under compression, right? So this origami is showing that hardening in the tension.
Right.
That's why tensile domain we were able to create solitary waves.
So this force displacement behavior is the entire structural behavior, or is the material constituting the material behavior?
Oh, this is more governed by the folding. So obviously there is some material elasticity also playing a role. For example, if we make this using different materials, it's going to show different responses. But mainly, this is due to the folding and governed by crystalline. So if you have different design of creases, you can definitely tailor all these curves. You can even make it bistable, monostable, So that's primarily governed by the torsion. And the way that we model this is basically we have a more like wireframe model, truss model. So each crease is replaced by linear element, just a truss member. And that also we account for the angular change between the faces, and we also implement torsional spring. So that's how we model this. But material effect is also playing a role. But given specific origami, we can basically represent all those material effects into the representative spring coefficients along the members.
Okay, I see. Yeah, so it's more of the structural effect of the Origami structure. Yeah. Okay, all right. Yeah, thank you.
Yeah, thanks for the question. But realizing this type of reflection wave mechanism, I demonstrated on this on this origami, but we could also show that in the 3D printed lattices. So we have a printed 3D lattice, chain of lattices, and we have shown similar wave dynamics as well. So as long as you can you can leverage this type of nonlinear response of material or unicell, this nonlinear wave dynamics can be realized in your setting.
Okay, I see. Okay, great. Yeah, thanks.
Great. So do you have a more question here? So feel free to unmute yourself if you have more question here. Okay, so great. JK, I actually have a following question after Yong. So for here, right? So for the 20 at the 30 unit cells, right? You have this in a row, and then you do this wave propagation, and then the my question here is, so actually you can combine different unit cells, right? Say you have different theta, and then you can form certain pattern there, and then to do more, I don't know, you know, to achieve, say, for more, say like a shockwave mitigation like that. Is that, I don't know, is that a way actually we can play with that?
Sorry, Jay, your question is
We can, you know, we can change the theta, right? So the unit cells, because unit cells, I believe, you know, in your the demo you are showing, right? So theta is all the same. Right? But actually we can change the theta, different theta, and then arrange them in a certain patterns.
So you mean
how well that can be affect this behavior, this wave propagation behavior?
Yeah, that's a good question. So instead of using homogeneous chain,
yeah,
if we have a heterogeneous chain, that's a very good question. And we have been computationally exploring, for example, that type of diatomic chain. Then we actually can have many interesting effects. To list a few, for example, we can have I mean, if by having, let's say, two different cells repeating, we can have something very similar to kind of a cascading effect, like turbulent flow. So starting from, for example, large wavelength and high frequency, then we can make the wave, like, for example, having, from large wavelength to small wavelength, and high frequency, so no, low frequency to high frequency. So kind of breaking the wave into smaller and smaller scale. So that's something that we can do. So here again, I mean, in my study, I'm more like focusing on keeping the wave into compact form. But again, by using different configuration, we can break it into very smaller pieces, like turbulent wave. Or we can also have something called like twinkling waves. And basically, wave front is leaving small oscillating pieces behind. So it's kind of, you know, like twinkling pattern, right, in the tail part. So that's all kind of interesting possibilities that we can leverage. So that's something that we can leverage, again, tremendous amount of work that nonlinear wave dynamics community has done. But they were not able to find the ideal platform to realize a lot of, you know, nonlinear wave dynamics in the solids, right? Origami can be a very successful platform, so that I think that I'm very excited about, you know.
Great. I have one more question actually about this stiffness. So for these structures, if you keep compressing, right? So well, the stiffness is gonna be going to increase again. I mean the slope, because you know, because we're keep compressing, right? And they're gonna become more condensation.
Right.
In that case, right? So the stiffness is gonna be maybe, you know, maybe increase again.
Yep,
so that means this situation gonna be correspond to like if you have a high speed impact wave, right, comes in.
That's a good point. So the whole spectrum, the whole domain of the curve will be like this, and it will basically go up, like, you know, it will have some plateau, then and it will have densification regime.
Yes.
So that densification would happen in a fairly large strain amount, at least, you know, like 60 or 70% of compression. But what we are exploring in this study is, you know, even the highest peak is 2% of strain, you know. So even here, it's this relatively very small compression that we have. Still, we can really see the effect of nonlinearity. And when, especially, but I mean, your point is also interesting. By having very strong impact, we may be able to hit this more like densification regime. Then I think we can probably have maybe some amplitude dependent wave dynamics. That's another exciting possibility that this type of structure can offer. Yeah.
Okay, great, thank you.
Yeah.
Do you have more questions from the audience?
Can I ask a question?
Yeah, sure. Okay.
Hello.
Hey,
Hi, Jake.
looking at the name, I thought, is it Yoon that I know?
Yes. I still get
You're
email from the
not
system.
with NC State anymore. Come on, are you supposed to join this seminar?
I still get emails from them, so it's great.
But I'm joking. It's so good to see you.
Yeah, you too. So it's very interesting talk. I was wondering, when you talk about the solitary wave, is there any way you can build a structure so you have like topological trivial and topological non-trivial, so you can kind of look at the interaction between topological physics and the nonlinear elastic waves, because we are very interested in that direction. Just not many people have looked at nonlinear waves in topological insulators. There are people in optics who recently got into that area, but not many people have gotten into that area for mechanical waves.
Mm-hmm.
Really nice way to generate solitons, which is very difficult to do in acoustics.
That's a very good question. So my team has looked into the combination of topology and origami. So I can share with you archive paper. We basically were able to experimentally see the topological edge mode in origami, and we can do the state transfer of edge mode from one side to the other by manipulating the origami. But that was purely in the linear regime.
I see.
So in the nonlinear regime, we will, how are we gonna, it's basically the marriage of very, very exciting three buzzwords, right? Topology, origami, and nonlinearity, right?
Exactly, yeah.
Nonlinearity part, we obviously, for example, like Vincenzo's work, like in the Lego set system, right? The topological soliton kind of behavior, that I think we can definitely show it in our system. But we haven't really got too much into that direction yet.
Okay.
Into the fader effect quite a lot recently, but to the nonlinearity, we only looked at more like very ideal SSH kind of system only, but not to the origami realm yet.
Okay. So we have a collaborator who's a physicist, and he has this really nice theory about soliton in topological systems. So if this is something you're interested, I can talk to him and then can follow up with you.
That will be exciting. Yeah, that will be exciting.
Yeah. Because we can do that using the acoustics. It's very hard to do.
We have a system which is a more, let's say, robust now. So I'm hoping that we can explore more interesting physics, including the nonlinear one now.
Okay.
But again, I think that has been all of our interest as well. So we have been looking into, for example, Anderson localization kind of effect with nonlinearity in the system. But again, experimental realization hasn't been much explored even in my team. But we believe origami can be one of the most feasible systems that we can realize that. Yeah.
Great. Thank you.
Yeah, thanks, Yoon. Yeah. Again, so good to see you.
Good to see you. Yeah. Great. Do you have more questions here?
Maybe I can ask a quick question. So this, I see this is quite a long aspect ratio, right? So would the Barconian could occur at some point?
Oh, that's a good question. But the way that we built the system is we have a center like a rod, which is penetrating all throughout the system. And each cell is having some sliding mechanism with respect to that cell. So it's the connection between the unit cells are not only through these face-to-face connection, but also there is, center rod. That way we
connect to the rod also.
Yes, yes.
Okay.
Yeah, that's a good question.
Okay, yeah, so if we have no more questions, so let's thank our speaker again. So thanks for the wonderful talk and a very interesting, very inspiring talk.
Thank you so much for the invitation again. And I look forward to meeting, some of you guys in a one-on-one meeting.
Yeah, sure. Okay, so the first meeting gonna start at 1 o'clock, so about half an hour later. Okay,
great.
so take a break. Okay, see you then.
All right.
Okay, I'll talk to you later.
Yeah, thank you.
Great, thanks, JK.
Great, yeah. See you.